sort of. And some people don't have their cameras on, so I guess they're, oh, there we go. Okay. So, you know, let me just say that there's a lot of people who sail very, very well and are very competitive, but don't really understand it. Those are kind of the seat of the pants sailors. And actually, because sailing is a lot of art combined with science, you can actually do pretty well if you're an artist, you know, which is kind of, it's not too satisfying for me as an engineer. Because on the other hand, you can understand entirely all the physics and be a crappy sailor because you don't have the hand-eye coordination or whatever it is. But as WPI students, you should want to understand what's going on. And so that's the reason why I'm going to chat about this. And I warn you right now that this is the sort of thing that I used to do on day one of instructional sailing, which I taught for 20 years at WPI, I guess, before I retired. And I could do it just on the board and everything. I'm trying to do something like that, but it's not going to be very good, I don't expect. But bear with me. But the important thing here is that if you guys have any questions, a lot of you are experienced sailors. I want to add some content. Feel free. And so I'm going to struggle with this a little bit, but I'm a big proponent of active learning. So if you don't understand something or you want to contribute some comment or something, you know, I'm just going to say, do it. So let me see if I can screen share here and let's see what happens here. Okay, well, that's starting to do something. I'm going to figure out where I am here. I think I wanted to be up here. Let me see, that's not the where I wanted to be, but let's just get to, oh, there we go. Okay, hold on here. There we go. Okay. Can you guys see that? Uh-oh. Can you guys hear that? Yeah. Okay, good. Okay, so yeah, so first off, you should understand that I'm who I am. I taught here in the mechanical engineering department until I helped develop the robotics engineering department, and my you know, last dozen years or so with teaching is pretty much exclusively the RBE program. But I did, at least I may have told you that, I was the one that resurrected the WPI Sailing Club back in about '95, and I taught sailing and coached the racing team for about 25 years until I retired last year. What you're seeing there, of course, is one of the editions of our international sailbot contest. If you guys don't know, this is an MQP project. We run it for 4 years. We've varied in international competition from coming in dead last to winning it 2 years in a row. And this boat you're seeing right here was one that we, the most recent winning edition. And by the way, that's on Quinsigamon Lake right there. So my background is, again, in academically, I have degrees in mechanical engineering and aeronautical engineering. And anecdotally, I also have about 4,000 hours of flying. I flew in the Air Force before I retired as a colonel flying C-130. So I know a little bit about aero stuff. So just to give you a little background about where I have been. My first boat, actually, I couldn't find a picture of it. It was a little 12-foot wooden boat that I built out of a Family Circle magazine. For those of you who have sailed Sunfish, it was a lateen rig, you know, which is a cat-rigged boat with a lateen sail, kind of a figure-4 sail. And it was made out of plywood. It was 12 feet long, and I was stunned that it actually sailed. I had that for about a year and then sold it. Then I bought this boat, and this was a 24-foot, about a 2,400-pound boat with a swing keel, so you could trailer it. And I learned a lot about sailing with this. My wife and I went on a bunch of week-long cruises up in Puget Sound in Seattle area. We were living in, I was actually working at Boeing Company at the time. And so this is the boat I had for many years and sold it. And then I bought this International 470 when I was going to graduate school. For those of you who, this is the boat, the one on the right is the specific boat that I used to do all the instructional training on. And so it's like a 420. Have any of you ever sailed 470s, by the way? I'm guessing no. Okay, a 470 is like a big 420. It's, but it is a trapeze boat, like the, you know, most of the Club 420s aren't. And so it's a lot of fun, and it's what I used to use for, I still own this boat. I've owned it for about 35 years, I guess, or so. And then when I went to Hawaii, I had a Hobie 16, which again, they're a lot of fun. especially if you're in the surf conditions. The whole time I was in Hawaii for 2 years, we had a lot of fun with that. It's probably the most robust boat that I ever want to take out into the surf because no centerboards to break, you know, and the rudders kick up when you hit the beaches, and we really abused that boat. It was a lot of fun. We used to have to re-glass the bottom edges of the sponsons every year because we hit the sand so fast and so hard that it would just grind away at the fiberglass. But a lot of fun. I had that for just while I lived in Hawaii. And then this is the boat that I spent most of my time on. When I retired from the Air Force in '97, my family and I moved aboard this boat, and we spent about a year of sailing around South America, Caribbean, about 9,000 miles or so. This is the actual boat that we owned right there. Beautiful boat, absolutely spectacular. And if you look here, you'll see I have a WPI Sailing hat on, by the way. This is when I first bought the boat, and it was just on our delivery cruise back from Annapolis, Annapolis up to Newport, so I could start working on it. So we hadn't done much to it then, but that boat I owned for a couple of years, and ironically, we sold that in '99, and 20 years later, last year, a guy in California called me up and wanted to know something about Tiana 52s. And so we started comparing notes, and he wanted to put on the same sort of self-steering device that I had. And lo and behold, it is my boat. And so I went to see him last year, and we sold it to a couple, and 18 years after they owned it, they sold it to him. And so I got back on my boat again. It's been named twice since then, but it's a good boat. This is my latest boat. And I don't know if any of you guys have ever been ice boating, but it's, I haven't yet. This was given to me. It was a derelict boat, about 60 years old. I completely refinished it. Everything on it now is ready to go sailing. I just need some ice. But the common feature of all these boats, of course, is that they all have sails and they all operate on the same principles, although their speeds vary quite a bit. This DN boat, I guess the record speed for these is for this particular class of boat is around 73 miles per hour. Typically, they will do about 4 times the speed of the real wind, and so it's very common. I mean, if you get 10 knots of breeze, you can almost always go up to about 35 or 40 miles an hour with them. So, looking forward to that. Okay, so now, bear with me. That was my background, and so in general, I have about 10,000 miles of sailing, and I figured out I have about 1,000 days of sailing. So I've been around a bit there. Now let me see if I can figure out how to get to my other slides and start the lecture part here. If I can figure out how to do that. Are we still? Everybody still with me? Got sounds of silence in here.
Yeah.
We're looking at a.
Yep.
You're looking at a what?
It's the last slide of your PowerPoint.
Yeah, I know. I'm trying to figure out how to get out of this into my other. Here we go. Wait a minute. No. Let's just cancel this, and I need to get to. My other. Oh, I know. I have to go back. Okay, so I need to. I think I need to stop sharing. And rip. There we go. Let me get rid of this. I told you this is going to be rough. I'm trying to figure this out. Okay, here we go. So I'm going to stop no, actually, I'm just going to go to a new share. Here we go. Now then, let's see if this is going to work. Okay, let me just quickly get this thing on here. It should come up. There we go. All righty. Okay.
Yeah, that looks like it.
Hold on. Yeah, I can get rid of this thing here. How do I get rid of that thing? Get rid of. There we go. Okay, so now you guys got this?
Yeah, looks good.
Okay. So let me see if I can get this thing a little bit bigger here. Whoops, I guess I can't do. Anyway, so here we are. I'm going to start with the forces involved with sailing here, and we got to start out with the fact that you should understand that a sail is nothing but a one-sided wing. It's a single surface wing. In fact, if you look at the Wright brothers airplanes, some of the early airplanes, they were just like that. And so we're looking down on a sail or across on a wing. It doesn't make any difference. Now, solid wings, and of course, more and more sailboats are using solid wing sails, act the same way as these wings do, but we're going to simplify it just by talking about what you're expecting to see here. So if we look at this, we need to label a couple of things here first. We have the, let me see if this is going to work. Yeah, this is the leading edge of the sail. And so those of us who are sailors would call that the luff. And then, of course, here's the trailing edge here. And what's that called, guys?
The leech.
Yeah, leech. Okay, very good. And so the distance between these guys is called the chord. So wings are defined by a chord versus span, so a length versus width. Okay, now then, if we look at this, if we actually get into a situation where we have some wind, and let me get rid of this. So if we say we have some wind coming from, like, oops, come on, why aren't you doing this thing? Okay, let's go here. Uh-oh, there we go. So let's say we have a wind coming like this. Now then, what that does is that results in some distribution of pressure, which will look sort of like this. And so there's a law that says that it's Pascal's law that says that pressure exerts normal to the surface. So it means that there's going to be a low pressure area which is going to put some forces like this. Now, there is a bit of a high pressure area here in the bottom, which will have some very small forces like this, but trust me, the lift of a wing or lift of a sail is not dependent upon the windward side of the sail. It's dependent upon the leeward side of the sail. It's really important to understand that the lift comes from the leeward side. That's what's presenting the lift. That's the reason why on every airplane in the world, when you see airplanes flying like military aircraft, and you'll see that they have things hanging on the wings, they always hang them on the bottom. The bottom of the wing is not important. It's the top of the wing that has to be perfect. So when you take this all into consideration, oops, oh, that's interesting. Here we go. When you take that into consideration, you're going to end up with a net force, and the net force is going to be somewhere like this. That would be just bigger here. The net force is going to be something like about this. And so this is the net aerodynamic force that comes off of a wing. And so the cool thing about that is that you can break it down into a bunch of components depending upon what you're interested in doing. And typically in aircraft things, what we do is we look at the difference between this free stream angle here. Oops, come on. That's a free stream angle, and you can break into a vector which is perpendicular to that, and that's called lift. So you can imagine if this was a airplane, that would be the thing which is lifting you from the free stream of the air. This is the free stream of the air. In sailing talk, that's called the apparent wind. That's called the apparent wind. And so this produces a net force like this. And it can be broken into components. One which is like this, and then of course there would be a perpendicular component like this, and this would be called the drag. And so the net force produces lift and drag, but you can break that net force into any components that you want to. And so this is the basic aerodynamic forces. Now, the thing about that is that we can calculate this out, and for those of you who are MEs or arrows, are there any arrows, by the way, in this group? Any arrows?
Yeah, I'm arrow.
Oh, is that right, Sarah?
Yeah.
Excellent. Well, I have a master's degree in aeronautical engineering, and I hope you're not astro. Are you astro or arrow?
I am astro.
Oh, boring. There's no beauty in astro. It's just oh man. Oh, well, anyway, you might as well have a water pistol. But okay, so here we are. Arrow is wonderful. And for those of you who understand arrow, and I'm sure you'll have something on that, you understand that you can define lift, and lift is equal to this thing called the coefficient of lift, which is a character of the shape of the wing or the sail. It has to do with the camber, the amount of curve, where the curve is, and it's also sensitive to Reynolds numbers. What's Reynolds numbers, Sarah? Do you remember Reynolds number?
I haven't gotten there yet.
Okay. Well, Reynolds number is a complicated thing that has to do with the kinematic viscosity of the fluid, and also the length that the fluid has to travel And so it's really important when you try to do wind tunnel testing of sailboats or of airplanes, because the Reynolds numbers don't scale like everything else is. But anyway, so it's a factor of coefficient of lift, and then of course it's times the area, because if you go twice as large a sail, you'll develop twice as much lift. Makes sense? And it also then has to do with the viscosity of the fluid. So air is pretty thin, and if you use a thicker fluid, you get more lift. And then finally, because it is a dynamic equation, as you would expect, it has to do with v squared over 2. V squared over 2. So that's the velocity, the free stream velocity divided by 2, and then you square that. So it's clear when you're sailing, when the apparent wind goes up by double, the forces on your sail go up by 4 times. And we all know this. Everybody who ever goes to windward will be going to windward, and your apparent wind is in your face, and you're feeling a lot of pressure on the wind, and then you turn downwind and says, what happened to the wind? Because your apparent wind drops dramatically, and when it drops in half, then the forces on your sail drop by 1/4. And so it's dropped 4-fold. And so it's really important to understand that the lift, the drag, the lift, the resultant forces on a wing are affected by the velocity squared. Now, there's another factor here which is really quite important, is that if you look at the difference between the chord line and the free stream direction, this area, this is called the angle of attack. And we're going to call it alpha. And the angle of attack is the direction that the chord line, which you could call the boom in your case of a mainsail, that's the angle between the boom and the apparent wind. That is the angle of attack. And of course, the thing about coefficient of lift is that it actually, coefficient of lift, it has kind of a linear relationship with angle of attack. And so it's very, very linear for a while. We're going to call this linear portion coefficient of lift prime. And so therefore, we can say now then that the lift equals the coefficient of lift prime times the angle of attack times the area times the density of fluid over v squared over 2. So it means if you double the angle of attack, the more angle of attack you give, you double the lift. And this makes sense until you get this whole area over here where you start to stall. And so too much angle of attack, and we all know this from sailing, you know, if you have telltales on your sails, and when the lured ones are starting to flutter and go backwards, that means it's stall, which means the coefficient of lift is really bad. There's sometimes you want that to happen, by the way, but this is the way it normally works. So before we go further, any questions on what we're trying to show here?
Yeah, I have a question about, so for the, I guess the angle of lift, how does this change when you have a jib involved?
Ah, okay. So this is really good, and you guys are already you'd be normally talking about, this is lesson 2, but I'll tell you what happens. You know, if you look at the free stream of the air starts, you can see the angle we have right here. This is the angle here that the air is coming in at. As it comes around the wing, it has a downwash, and so the angle will be changed slightly. So if this angle here, it will be instead of being like this when it comes off, it'll be something like this. And so the angle will change by some degrees, which means now then, if this is the jib, that means that the mainsail now has a different free stream angle than the jib, which means that you have to preserve a proper angle of attack, it must be sheaved in a lot higher, a lot tighter. And of course, on most overlapping jib boats, you will discover that for your best windward capability, the boom will be basically on center line, which doesn't make sense. I mean, if it's a cat rig boat, like a laser or a fin, that won't happen. But with an overlapping jib boat particularly, it turns out that you will have changed the wind vector and it will have come up there. Now, anecdotally, you should all understand, the most efficient wings do not have a jib. The advantage of a jib in general is to broaden the range of angles of attack that you can cover. A super fast boat that's designed for incredibly high lift over drag will never have a jib. If you look at the fastest sailing craft in the world, which are doing like 120 miles an hour, these are the ones on ice and on land, there's no jibs. Because their apparent wind is running at about 10 degrees from the bow, 8 to 10 degrees. And so they don't need it. They're incredibly efficient. But a jib has a couple things. Number one, it allows you to balance the boat better. And we'll talk about balance a little bit later on in this lecture about balancing weather helm and lee helm and this kind of stuff. But it also allows you to go deeper into, you can have deeper angles of sailing and keep it aerodynamic. So there's some answers to that, but that's what we did. Okay, any other questions about how wings in general work?
Yes, actually, I have a question about the twist of the mainsail that you mentioned, boats with the mainsail and the jib.
Yes.
If you see those boats, generally you have the boom on the middle.
Yes.
And then you have on the upper side of the sail, you have a lot of twist, having an angle of attack larger in the upper side of the mast. Why you want that?
Oh, the twist. You're talking twist, right?
Yeah, exactly.
Yeah, okay, excellent. Okay, right. So if you look at, there's two reasons for twist. Even without a jib.
Yes, actually, I learned that for sailing, I learned that you want twist when you are in an overpower situation, when you can't handle the boat. You really want to have a lot of twist to have the top of the sail just.
It can be used for depowering. You can depower because obviously the heeling moment is much higher, much larger at the top of the mast than it is at the bottom of the mast. So if you develop too much power at the top, then you'll heel excessively and that slows you down. However, aerodynamically, even without excessive heel, there's a reason for twist. Imagine a boat is anchored and the wind is coming from 90 degrees. Now, that means that the boat is not moving, the apparent wind and the real wind are the same, which means everywhere along the height of the boom or the mast, it's the same direction. But if you know anything about, let me see if I can, if you know anything about the way air travels, if you look at a surface like this, the wind slows down the surface and it builds up as you go higher and higher. It's called the ground effect. And so if you can imagine a sailboat sailing here, alongside here, the velocity is higher at the top than it is at the bottom. So now when you take the anchor off the boat and it starts to move forward, you no longer see the real wind, you see the apparent wind. Now, your velocity forward is the same at the bottom of the mast as at the top of the mast, but the wind velocity is not. You get the idea here? So the wind vector changes more at the bottom than it does at the top. And so that means that the wind starts shifting more to your bow at near the surface of the boat because the true wind is not as high a velocity as it is 20 feet up. And so this is the reason why aerodynamically twist is important, even if you don't have a jib. Now, the truth of the matter is if you have like a 420 or 470, any fractional rigged boat, that the vectoring of the air, which causes the backwash off the jib, does not affect the top of the main. And so you need to have twist up there because it's seeing another different wind than because the jib hasn't interfered with it. So it sees it doesn't see the turning of the wind. And so there's several reasons for that. That's a very good question. But twist is, in any case, twist, no matter what you're talking about, is always better than no twist. There's never a time when the wind velocity is exactly the same at surface as it is 20 or 30 feet high. And anytime there's any difference in velocity, it'll always be more at top. That implies you should have some twist, jib or not. But with a jib, you need more twist. Great question. You guys know a lot about sailing. This is good. Any other questions?
Yeah. So I've heard basically the most efficient tack, or sorry, like point of sail for a boat is a beam reach, and that makes sense because of like how the vectors work out. But I heard that's not true for an ice boat. I don't know. I want to know the physics of why and what that.
Okay. So you guys are jumping ahead. This is great. Is that it? Zoe? Yeah, Zoe. Anytime you have on ice boats or also on hydrofoil suspended boats, they have such low drag, it takes very little thrust to go forward. And so as soon as you start going forward, it starts shifting the wind further and further. Their parent wind becomes more and more on the bow. And so what happens is that the more apparent wind, the more your apparent wind shifts forward, the more your velocity adds to its velocity. And so it really becomes a fact that there's a trade-off, and it probably is around, it's probably, if you look at the AC boats, they actually go fastest when they're going downwind. And even though they're on a broad reaching course, if you were on the boat, it's close reaching. Because the apparent wind, even when they're going downwind, it's only about 30 degrees off the bow, even when they're going downwind on like a 150-degree angle. Because they're going so fast that the relative wind shifts forward. So in that case, they go fastest when the apparent wind is shifted to about 30 degrees, which is not what you and I would think is a beam reach. Now, if you looked at the geography of it, they're actually on a broad reach. But reaches are defined by apparent wind, not by real wind. And so if you have a very, very fast boat, like an ice boat, you will find out that they go fastest when they are proceeding downwind, but it actually is a close reach from the apparent wind. If you look at my, it's mysterious because when they jibe, for example, same with the ice boat, when an ice boat jibes, the wind doesn't come across the leach of the sail. They're going so fast that when you jibe, the wind still stays forward of the bow. Mysterious, isn't it? And you can especially notice this if you ever look at any of the new AC boats, is that the only difference between, the only apparent difference you'll see in the sail configuration when they're going downwind or upwind is that they will put more camber into their solid wing when they're going downwind. And so they have a two-piece wing, and they'll actually put a little more camber, crank a little more camber, but the jib will look the same. It's probably just a few degrees more open. But they never use any spinnakers because it's simply, they never on a sail angle where you could use a spinnaker. The wind is always coming way forward of the beam, always closer than 45 degrees from the bow when they're sailing any point of sail. And the same way with ice boats. In fact, ice boats have sheeting arrangements that don't allow them normally to go beyond about 45 degrees off. That's as far as you run out of sheet, because there's no need to ever sail with the boom any more than 20 degrees off center line. And so and because you're dealing with very high speed wind conditions on an ice boat, you normally have, even on my little DN, I think it's only a 65 square foot sail, but it has a 6-to-1 purchase. On a 75 square foot sunfish, you have a 1-to-1 purchase and have no problem hauling it in. But on an ice boat, because the relative wind speed, typically you'll be having 50 knots going across the sail when you're doing 35 or 40 knots. And so you have to have an incredibly strong purchase on the main sheet, which means that there's gobs of main sheet to haul in. And so you can never really let them out beyond what would look to be a close reach. It's a different thing. In fact, it's if you've never sailed a boat that has that sort of thing, it's pretty weird. I'm looking forward to it. And I'll take everybody up if we get some good ice this year. Okay, any other questions before we slide on to the next slide here? These are excellent questions. It's really fun having you guys interact, so please feel free to keep doing that. Let's see if I can get to the next one here. Okay, so now we figured out that this is what the sail looks like. That's what a wing looks like. Now let's lay a boat on here and see how that all works. Hopefully I can hope this thing is gonna work for me here. So let's just say we're at a let's just say we're gonna be at we'll be kind of a close haul condition here. So we're gonna be sailing along in this angle here. So let's put our boat in here. Okay, so now we still have this angle of attack here. We still have this. This is the angle of attack of the wing, and now then let's divide this resultant force into two other vectors. So we can divide it now into a vector which is along this path here, and then a one that's along this path here. Now then, so here we have this part here is thrust. This is the part that's trying to move the boat forward. And then this part here, this would be the leeward force, which is going to cause heeling. Not cheering, heeling. That looks like cheering to me. Okay, so now we can see that, and now if you look at this, we can look at this angle here to here, and this is what we call the sailing angle. the sailing angle. In this case, it looks like we're on a, I'd say we were close, yeah, kind of a close hauled or close reach, port side, right? And we're on a port, you know, close reach. So we're about 60 degrees off the wind. And you can see there's a sizable percentage of this wind force that is actually thrusting us. And then there's quite a bit that's trying to bring us back, right? It's trying to heel us over. Now, this is interesting, except that, and by the way, if you think about it now, this would be kind of, this right here would be pretty much the boom here. This is what we're kind of thinking about, the boom extension. This is, we're talking about a cat-rigged monohull here. Now, what counteracts the thrust? Well, you know, we're going to do some static analysis here. We know there's going to be some drag here. What are the two kinds of drag that can happen with a boat, the hull? Anybody know?
You have drag from the water.
Well, yeah, okay, that's skin drag. It's called skin, right? Skin friction. What else? What's the dominant force of drag once you go going fast?
Friction?
Not friction.
Displacement?
Yeah, Lisa, it's displacement. It's called wave drag.
Is that the thing of like, you only can go as fast as, like, your wake is only as long, or your wake is only as big as your boat is long or something?
Yes. The hull speed of a boat is roughly 1.3 times the square root of the water line in feet. And so what this really is saying is that the drag initially is just skin friction drag. And that is a factor of how much area of contact there is between the water and the skin, which means if you have a flat planing boat like a 420 or 470 or laser, at low speeds, they're much faster if you heel them. Because the more of the hull you can submerge into the water, the more it becomes like a canoe. A canoe has the minimum hull drag, the minimum skin drag. A semicircular hull shape minimizes the surface compared to displacement. But once you get above a certain speed, which is roughly, you know, by this speed here, now then what happens is the bow wave is significant to the point where the next bow wave, because the bow wave goes through the water at this relative speed, is that you have a wave coming off the front, and then but once the second wave gets to the back and you try to go faster, this one starts going behind the boat, and now the boat's going uphill. Until this time, it's balanced between the two wave crests. But once this one starts to go further back, which means you're going faster, this one stays where it is. Now then, the boat actually has to start going uphill. And this is when you either are stopped or you have to start planing. And this is so noticeable. If you've ever been in a ski boat, you know, you're like a 16 or 18-foot ski boat, it takes a lot of thrust and the bow is way high until all of a sudden it gets on the plane. Then all of a sudden you can power the engine back because the drag dramatically reduces once you've got above planing speed. So a flat bottom boats are designed to plane to get through this, but a heavy displacement boat can never you know, get hydrodynamic lift enough to get it to plane. But at any rate, so you can see now that this is going to equal this when you're in balance. Now, but what equals this? What balances that?
Your centerboard or keel?
Yes, because here's our second surface. We have a surface under here. It's another symmetrical foil, and of course it has to develop a force here that's equal to the force on the other side. It has to, otherwise the boat's imbalance starts accelerating to leeward. Now how can it develop that force? It's a symmetrical hydrofoil. And now let's take a little break here. Let's talk about lift again. And we've been talking about aerodynamics. Tell me something, what's the difference between aerodynamics and hydrodynamics? What's the difference between fluids when it comes to pneumatics versus hydraulics? Give me the essential difference between the two fluids.
So a pneumatic system or air system has like a compressible fluid, whereas a hydraulic system has a non-compressible fluid.
Nick, that's exactly the answer that I was hoping you'd give me. But guess what?
You You can kind of compress water. I mean,
Nope. Well, you can, but it's insignificant. But here's the deal that is amazing, you know, and I'm sure that our aero will understand this, is that air does not start to compress until it doesn't know you're coming. When you walk through a room, the air in front of you does not compress. It gets out of the way. Because it hears you coming. It literally hears you coming. It literally senses you coming. And in fact, the low energy, the least energy it can do is just simply slide out of the way. Because remember, a gas will fill in any capacity without having, you know, it just fills every space. And so it's super simple for it just to get out of the way. And it does that. And so if you were actually to measure the density of the fluid over a wing or a sail like this, you'd find the density is identical everywhere. So in aerodynamics, air is considered incompressible. The only time air is considered compressible under two occasions. Number one, if you're in a confined space like a closed pneumatic system, or number two, when the object doesn't hear you coming. And when can that happen? When does the air not know that a wing is coming through it?
when you're moving really fast.
How fast?
Speed of sound?
Yes. And so compressibility effects, which is what causes sonic booms, only occurs when you get to the speed of sound. That's the only time, and it's the compression wave that makes the sonic boom, because the air cannot get out of the way. It doesn't know you're coming. All of a sudden it gets crushed, and that causes this sonic boom. And so this is the reason why the shape of airfoils for subsonic flight and the shape of hydrofoils are virtually identical. In fact, in sailboat, we use the exact same NACA section for our keel and rudder as we do for the wing. It seems stunning when you think about it, but it really makes sense, because the air acts just like water in terms of compressibility, because it doesn't compress. And so this is the reason why when you study aerodynamics, often they use water tables with dye to analyze shapes, because it behaves the same way. It stalls the same way. Everything happens the same. Okay, but now think about the keel. Remember, we had this thing about the lift was going to be, coefficient of lift times area times density times v squared over 2. The density of water is 700 times more dense than air. So what does that mean about the area of the keel compared to the area of the sail?
It can be much smaller.
Yeah, but if you do the analysis, you'll find it's not 700 times smaller. Because here's where you have to understand that the coefficient of lift, even with the identical shaped airfoil, is not the same with a fluid that has a different viscosity than air. And you have to deal with Reynolds numbers and a few things, but you'll find out that the reason why typically a keel will be it could be, and by the way, the velocity, of course, is different too, because the velocity we're talking about is the air velocity for the wing and the water velocity for the keel. Now, in most boats, the air velocity is faster than the water velocity, but not on a high-speed boat. Like on an America's Cup boat or on an ice boat, the water velocity is actually faster than of course, we don't have keel to worry about on an ice boat, but on a hydrofoil boat, you'll discover that the velocity through the water, it actually won't be faster than the apparent wind. So the apparent wind will always be a little bit faster than the other wind, but the main difference is kinematic viscosity, which changes that. So that means that in order to develop lift, we must have an angle of attack here.
Is that velocity number, is that speed over ground or speed made good?
The velocity, so far, every velocity we've used is apparent velocity to the wing surface. So it has nothing to do with speed over ground. It has nothing to do with the real speed unless you're anchored. Because the wing does not know whether you're anchored or not. All it does is the wing sees the air. And it doesn't care whether you're anchored or not. It just sees the air. It sees the apparent wind. That's all it ever sees. Okay, but you should understand, for the keel to develop this, there has to be an angle of attack here. There must be a keel angle of attack. There has to be a keel angle of attack. What's that angle of attack? What does that do to the boat? In order to develop an angle of attack with the water against the symmetrical keel, what has to happen with the boat? Will the boat sail in the direction it's pointed?
Not quite. Doesn't the boat have to be at like a little bit of an angle?
It has to, yeah, at least it has the angle, it's called leeway, of course, which means that, you know, I'm headed, I see where I'm headed, but the boat will never be going quite that direction unless there is no leeward force being generated. Anytime there's any leeward force being generated by the wing or the sail, that means that your boat will never go exactly in the direction you're heading. It'll always be a few degrees off. And that few degrees can vary from, 2 to 5 degrees to over 15 degrees if you try close. If you're really trying to beat into the wind and getting as close as you can, you'll discover you have an incredibly high angle of attack on the keel, and you may even stall the keel, which means you could just be going sideways. But it is, if you, the higher you get to the wind, the tighter you get to the wind, the more leeway you develop, because the angle of attack has to increase on the keel. Now, the keels for centerboards, for example, are really prone to this, because centerboards like the 420 or presumably the Hunter has a centerboard. Retractable centerboards have flat parallel sides with just a little leading edge camber and a little trailing edge bit, which means they're not a very efficient wing. They will stall pretty early. So the most efficient underwater bodies are dagger boards, which can have a beautiful shape. They don't have to retract. They have a beautiful shape, optimized airfoil shape all the way through. Or a fixed keel, which they can also optimize shape. But the centerboard never has an ideal shape because of the nature that it has to retract. It means that it's going to be normally have a major portion of its section will be just flat sides, parallel flat sides. Okay, so this means that we are going to have this keel angle of attack, which is called leeway. Now, if you think about that, that means that this lift, this force coming off of the keel can also be divided into two vectors. One, which is going to be a direct counter to the leeway, and then another one, which is actually going to be what's called induced drag. This will be a very small, but there'll be a little induced drag by the keel also. The same angle here will be the angle that the keel angle of attack has. So again, the more you cheat into the wind, the higher the drag that is developed by the keel as well. Now, the final thing we should talk about before we call this session quits is that if I look at these resultant vectors, and let me see, I'm going to make them a little bit brighter here so I can figure out. So we have this resultant vector and this resultant vector here. What did they do for a moment? Let's say we put a moment about, let's just draw a moment about, let's put a moment right here at this point right here. We're gonna do this as a center point here. And so we can see that this force has no moment here, so it has no turning moment. This heeling one generates no turning moment about this point. The drag on the boat also is pretty much on center line, so it develops no moment. But what about this one here? It would turn the boat like this. Can you see that? Can you understand how the effort of this blue vector, because it's aft of this arbitrary turning point, would tend to cause a positive rotation around that axis?
Leeward
What
helm?
is that called in boat terminology?
Leeward helm?
Well, that's 50-50 chance.
Oh, windward helm.
Weather helm?
A weather helm. Because look, it's going to turn the boat positive, which is counterclockwise. Counterclockwise brings the bow into the wind. So how do you counteract that? Well, you have to have one more wing, right? You have to have a wing back here. And it has to generate a force like this. And the way it can generate a force like this is by your tiller moving this way. Because then this one times this moment arm would counteract the other one. This is the reason why when you go to windward, you always have to put a little pressure on the tiller to balance the sum of moments. Is that understood? Now you can affect this by changing the location of the keel. The further the keel is aft, the less this turning moment exists. And by the way, if you put a jib on the boat, it moves the aerodynamic forces forward, which also change that, makes it more balanced. This is the reason why if you want to steer a boat without a rudder and you have a jib and a main. If you want to go upwind, you ease off the jib, and then it develops weather helm. If you want to go downwind, you ease off the main, and now it develops lee helm, and it turns clockwise in this case, or goes downwind. Now, I'll just leave this one last thought, is that all of these sketches are if the boat was upright. It's a three-dimensional problem. When the boat heels, what happens to the moment arm of the wing vector, the sail vector? Think about it.
That vector would
Pardon?
that vector would be decreasing since the angle
Here's what you need to think about. I mean, thank you for giving it a shot here. But here's what you need to think about is that the let's just do this color here. What happens is that this point right here, as you heel, moves in this direction. Oops. Come on, don't do that. Oh, it did it.
So wait, it would decrease because you're coming out of the higher. Your more of your sail is in the slower moving part of the air column.
Yeah, except that the significant part, which is good, Sam, because there is a bunch of complication here, but the most important thing is that the entire center of effort of the sail moves to leeward, which means that the turning moment increases. This is the reason why when you roll tack, you hike it, you let it go way to leeward, and that helps it turn. It wants to spin right into the wind then, because the center of effort is way off to the right, to the leeward side of the boat, which means that it pulls the boat around to windward. And so this is the reason why this sum of moments problem is a little more complicated now. Well, I've taken plenty of your time, I think, here. I would answer any questions you might have about what we talked about now. And then, and I think we've probably done enough as far as new information. But just understand the sailing features, first off, is that a boat will never sail in the way you are pointing it unless it has. Some boats have what's called jibing centerboards. International 14s, for example, the centerboard actually has a slight pivot to it. So when the pressures on the board occur from the leeward load, it actually cranks it over so it develops angle of attack. And so in that case, International 14s are designed to sail straight if they have that jibing centerboard or dagger board. And then the other reason why if you have individual dagger boards, like some of the ocean races where they use the keel only for ballast, shifting ballast, and they have dagger boards that go down, those dagger boards are not symmetrical. They only use one side for each tack, and it's designed to have a positive angle of attack so the boat will be at its minimum hull drag by going straight through the water, because the angle of attack is built into the dagger board. They have a port dagger board and a starboard dagger board, and those are designed that way. And by the way, the Hobie 16 that I showed you, the beach cat, the classic beach cat, doesn't use dagger boards or keels, but has asymmetrical hulls. If you look at the hulls, you'll determine that the hulls are flat on the outside and they're curved on the inside, which means that when you're flying along on one hull, you actually have a camber surface which is lifting you in the windward direction. And so the hulls are not symmetrical. The hulls are asymmetrical so that they actually, when there's only one hull in the water, it always develops a lift toward the other hull. Okay. So anyway, so understand that the boat any boat you guys normally sail, it will always have an angle that has to be there to develop an angle of attack of the keel. And the harder you come into the wind, the more leeward force is developed by the wing, the more force has to be developed by the keel. And by the way, it's clear that the sail force causes heeling. What is the force on the keel cause, or on the centerboard? What force does it cause heeling? It's underwater, it's pointing the other direction, which means about the center of the boat, it also causes heeling. And this is the reason why you've got to move your butt, because both of those lifting surfaces are conspiring to tip the boat over. Anything underwater is developing force toward the wind, which is trying to tip it away from the wind, and everything above the water is trying to develop force away from the wind. So both the keel, centerboard, and the wing are conspiring, trying to tip the boat over. Now, a ballast keel, of course, has ballast trying to do the opposite, but we don't normally sail with those on our, in this class. And so your butt has got to do all that stuff. Any other questions? Okay, Lisa, I think I'm finished. Oh,
For the sailbot, do you use a ballast keel because you don't have anybody on it to hike out?
oh man, you asked a great question there. We don't use a ballast keel. We use a movable ballast on top. It is very, very clever. It is, and you may not be able to see it here very clearly. Let me see if I can get it to be a little bigger here. Come on. Oops, back. Yeah, right here, that's 12 pounds of lead, and it's on a carbon fiber arm. It's operated by a motor up here. So right now, you see it's moved over off center line to the starboard side because we're on a starboard tack. And so this is, whoops, doggone, keep moving that. There. Yep. And so yeah, this is that's how we do it with the sailboat. It also has 15 pounds of lead on it on the bottom of its keel as well. But this is our own innovation. We're the only ones that do this movable ballast, and it works pretty well. You guys see the telltales. You know how to read these, right? So what do you think about this sail set? Is it set properly or not?
Looks pretty good to me. Telltale.
Yep.
Back.
Yeah, it is. It does have a bit of twist, as you can tell. If you look here, this is pretty close on center line. You can see, oops, doggone, I keep going the wrong way. And it does twist off at the top. You could use a little bit more luff tension, right? But that's the only way we could make this sail. It wasn't that great. But anyway, it's pretty cool. So I encourage any of you guys that want to get involved academically just to jump on the sailbot team. We actually have room for people that we have 6 people on it now, but we always have we're always looking for new people to join into it to help out and let it become their MQP when they get around to it. We have MEs, RBEs, and arrows on it right now, and CS as well. Okay. Any other questions or anything for me, guys?
Kristen says hello.
Oh, really?
She does, yeah.
Where is she?
She's in Florida right now, but she's coming to Worcester in B term.
All right. Well, I'm glad to see her. Hopefully. Well, we're still. I guess we're still locked away in B term. I guess still. I think, right?